Welcome, aspiring programmers. Today, we're going to embark on an exciting journey through the world of sorting algorithms. Sorting is a fundamental concept in computer science, crucial for organizing data in a way that makes it easier to process, search, and visualize. Whether you're dealing with a list of names, a collection of books, or a dataset of astronomical objects, sorting helps you manage and understand the data more effectively. We'll explore 5 different sorting algorithms, each with its unique approach to organizing data. Bubble sort. Imagine lining up for a group photo and swapping places until everyone is in the right order. That's essentially what bubble sort does with data. It repeatedly goes through the list, compares adjacent elements, and swaps them if they're in the wrong order. It's simple and intuitive, but not the fastest kid on the block, especially with large datasets. Selection sort. This one acts like a talent scout, searching through all candidates to find the next star, or the smallest, largest element, and then moving it to its correct position. It repeats this process until the entire list is sorted. While still not very efficient for large lists, it's a great way to understand how you can improve sorting by minimizing swaps. Insertion sort. Imagine sorting a hand of playing cards. You pick cards one by one and insert each into its correct position among the already sorted ones. Insertion sort does exactly this with data. It's efficient for small datasets or nearly sorted arrays and gives you a good perspective on how incremental improvements can be made. Merge sort. This is where things get really interesting. Merge sort divides the dataset into smaller pieces, sorts those, and then merges them back together in order. It's a classic example of the divide and conquer strategy in computer science, offering a much faster and more scalable way to sort large datasets. Quicksort, another divide and conquer champion. Quicksort picks an element as a pivot and partitions the data around this pivot, ensuring that elements less than the pivot are on one side, and those greater are on the other. It then sorts the partitions independently. Quicksort can work wonders with large datasets, combining efficiency with elegance. Understanding these algorithms enriches your toolkit as a programmer, giving you the versatility to tackle sorting challenges with insight into their time and space complexities. This knowledge is not just academic, it's highly practical. It can influence how you structure data, optimize applications, and solve real-world problems efficiently. Now let's dive into the code and see these algorithms in action. Bubble sort algorithm. The bubble sort algorithm starts by initializing a loop to ensure at least one pass through the array. Within this loop, we have another loop that iterates over the array, comparing adjacent elements. If the left element is greater than the right one, they are swapped. This swapping process continues until the array is fully sorted. The outer loop repeats this process until no more swaps are needed, indicating the array is sorted. The desired outcome is to sort the array in ascending order, ensuring that elements with lower values come before elements with higher values. Selection sort algorithm. Selection sort begins by iterating over the array using an outer loop, excluding the last element. Within this loop, it initializes a variable to store the index of the minimum element. Then it iterates again over the remaining unsorted portion of the array to find the minimum element. Once found, it swaps the minimum element with the current element in the outer loop. This process repeats until the entire array is sorted. The desired outcome is to arrange the elements in ascending order, with the lowest element at the beginning of the array. Insertion sort algorithm. Insertion sort starts by iterating over the array from the second element onwards. For each element, it temporarily stores the element and initializes an index to its left. It then compares the current element with the elements on its left, shifting them to the right until finding the correct position for insertion. Once the correct position is found, the element is inserted, and the process continues for the remaining elements. The desired outcome is to sort the array in ascending order by gradually building a sorted portion of the array from left to right. Merge sort algorithm. Merge sort recursively divides the array into halves until each subarray has only 1 or 0 elements. It then merges the sorted subarrays back together. During the merging process, elements from the left and right subarrays are compared and merged into a new sorted array. This process continues recursively until all elements are merged into a single sorted array. The desired outcome is to sort the array in ascending order by dividing it into smaller parts and merging them back together in sorted order. Quicksort algorithm. Quicksort selects a pivot element from the array, often the first element. It then partitions the array into 2 subarrays, elements less than the pivot and elements greater than the pivot. The function recursively applies the same process to each subarray until they are sorted. Once sorted, the subarrays are concatenated together with the pivot in the correct position. This process continues until the entire array is sorted. The desired outcome is to efficiently sort the array in ascending order by repeatedly dividing it into smaller parts and sorting them independently. In conclusion, when it comes to efficiency, applicability, and usability on large datasets in the context of JavaScript technologies, Quicksort emerges as the clear winner. Quicksort's divide-and-conquer approach makes it highly efficient, especially for large datasets, as it minimizes the number of comparisons and swaps required. Its versatility and effectiveness make it suitable for a wide range of applications. MergeSort also performs well on large datasets, offering a consistent time complexity, but it may require additional memory due to its recursive nature. Insertion Sort and Selection Sort, while simpler to understand, are less efficient on larger datasets due to their quadratic time complexity. Bubble Sort, on the other hand, is the least efficient among the algorithms discussed, making it less suitable for large datasets where performance is crucial. In real-world scenarios where performance is a priority, such as sorting large datasets in web applications, opting for Quicksort would be the most prudent choice. Its efficiency and scalability make it a reliable option for sorting data efficiently in JavaScript applications. Thanks for watching, everyone, and don't worry if you missed anything. We've added a link to the source code in the description. If you found this video helpful, please like and subscribe for more of the same. Thanks again. And remember, we're always learning, so keep coding, keep exploring, and keep building amazing web applications.